Welcome to EPG Pathshala on computer science. We are looking at computer networks. So, the module that we will be looking at today is on routing in IP. So, we will take a look at the OSPF protocol which is used for routing. So, the OSPF protocol basically uses an algorithm called link state routing algorithm. So, we will take a look at this link state routing algorithm and then we will look at the details of this OSPF protocol, which basically stands for open shortest path first. Now, remember that whenever we talk about routing in a network, we view the network as a graph, right. So, we model the network as a graph. So, where the nodes of the graph are the routers, the edges are the physical links, and associated with every link there is a cost. So, which could be based on various factors, it could be based on delay or congestion level and so on. Okay. And the whole process of finding a path boils down to finding a least cost path on this graph. So, that is the idea that we are using to find the route to go from any source to any destination. Okay. So, when we talk about this kind of a graph based approach, now the information that we could use could be either local information or global information. So, what we mean by this is that you could only use information that is available locally, that is without having a complete view of the network, get only information from your neighbors and use only the local information to construct the graph and to be able to find out the least cost path. So, that we have already looked at that kind of an algorithm, which is the distance vector algorithm, which uses only local information, which is based on Bellman-Ford algorithm, okay, and it is used for least cost Bellman-Ford algorithm for least cost path. The other option that we have is a global mechanism where every node will have a global view of the network. So, the link state algorithm that we are going to look at now basically belongs to this category, and it uses the Dijkstra's algorithm to obtain the least cost path. So, we will take a look at this one now. Okay. So, the strategy that is used in link state routing is that you have to send to all nodes, not just the neighbors, information about the directly connected links. That is, every node finds out which are the links to which it is directly connected and sends that information to all the nodes, not just to its neighbors. Okay. And it does not send its entire routing table, it only sends this information about its directly connected links. Okay. These two are the two key points to note as far as link state routing is concerned. Okay. So, now the resultant this process basically what it results in is that the routing information that is obtained, right, that is obtained in a global manner because everybody's information is given to all the nodes in the network, right. So, global information is available and it is made available to everybody by means of a process called reliable broadcasting. So, you need to broadcast it, but we use something called reliable broadcasting mechanism so that you make sure that everybody gets this information. And this whole thing is a dynamic process in the sense that whenever there is a change in the topology, okay, or even periodically this information is always exchanged. Okay. So, this takes care of the dynamic, in case there are any changes, there are any dynamic demands, that is also taken care of by this. And the path calculation is done using Dijkstra's algorithm. Okay. So, these are the key points that we have to understand with respect to the link state routing algorithm. Okay. So, let us look at this in detail. Now, we said that first every node sends information about its directly connected links, not the entire routing table. So, how is this achieved? Basically, what every node will send is it sends out something called a link state packet. Now, what is there in this link state packet? It will have the ID of the node which is creating this LSP, link state packet, and the cost of the link to each directly connected neighbor. If a particular node is connected to 3 neighbors, the cost of the link to each of those 3 neighbors, okay, that information is specified. And the sequence, a sequence number. For this LSP packet, there is a sequence number associated with it, okay, and there is a time to live field, which basically says how long this packet is considered to be alive in this network. Now, why do we use the sequence number and TTL? These are basically to aid in identifying which LSP packet is the latest packet, for instance, because remember LSP packets will be sent periodically. So, we need to always know which is the which carries latest information. The sequence number can be used to track that. And TTL is always used in order to make sure that a particular packet does not live for too long in the network. So, once it is stale, you would like to delete it. Okay. So, that is the way TTL is used in IP protocol. Similarly, TTL is used here as well. Okay. So, these are the fields that we have in the link state packet. Now, the second part is of the strategy that we had is that you send to all the nodes, not just neighbors, this information. So, now the information that we have is available in the form of this link state packet. So, all we have to do is we have to make sure that this link state packet is sent to all the nodes. We have to do some reliable broadcasting or reliable flooding as it is called. So what do we do now? When a particular node has its LSP, it forwards it to all the nodes but the one that sends it. Okay, when it has its LSP, it sends it out first to all its neighbors, and when a node receives an LSP from another node, it will forward it to all the nodes except the one that has sent it. Okay. So to make sure that you don't send back the same information back to somebody who has sent that information to you. Okay. So, and remember, we have a sequence number field. So using the sequence number field, you can always keep track of which is the latest information, the recent LSP from each node, and that information is what is stored. Okay. And every few seconds, or whatever period you choose, every few time units of time, okay, every few time units, you will generate a new LSP, and you will increment the sequence number, and you will send this LSP. Okay. Normally the starting sequence number is 0 when you reboot. Okay, and the TTL that we talked about. So when this packet is sent, LSP packet is sent, you will decrement the TTL at each stored of each stored LSP and discard when it becomes equal to 0. Okay. So now this process is what we are referring to as reliable flooding. We will just take an example to see how that exactly happens. Now let us say, for instance, a packet, an LSP packet arrives at node X. LSP, now what is the next step? What is it that X now has to do? X will now have to send it to A and C, not back on the path through which it received, but only to A and C, which are its other neighbors. So X floods this LSP to A and C, and what is it A and C will now do? A and C now will send it to B. Remember that A and C both will not send it back to X because they receive the packet from X. So both of them send it to B. Now B actually receives 2 copies of the same packet. So it keeps one, discards the other, okay, and it sends it to D, not to C or A, because it has already received packets from that direction. So it sends it to from which it has not received this packet, so it sends it to D. Once it is done, for this small network that we have, the flooding is complete. Okay. So you make sure that by keeping track of sequence number and making sure that you don't send packets out on the link through which it came, right? You make sure that the flooding will kind of get completed within a reasonable amount of time. So that's the idea that is used here. So reliable flooding is one important aspect of our link state routing algorithm. Okay. Now coming to the shortest path routing that is used. So we said shortest path algorithm that's used is Dijkstra's algorithm. So what is required for this is that the network topology and the link costs to all the nodes are known. Okay. Now remember that this reliable flooding of all the LSP packets takes place. So all LSP packets are sent to all the nodes in the network. So using that information, everybody has the same information. They can construct a complete graph of the network. So which is why we say this is a global information based algorithm. So complete graph of the network is constructed. So once a complete graph is constructed, then you just have to run the Dijkstra's algorithm to compute the least cost path from whichever node, from one node, from the source to all other nodes. So whichever node is now running this algorithm, from that node to all the other nodes, least cost path is constructed, and the forwarding table can be arrived at from that information. And this process is normally an iterative process. So after k iterations, you know the least cost path to k destinations. Okay, that's basically how it works. Okay, we look at this in detail now. Now the notation that we'll use some simple notation to understand how this algorithm works. So let's say C of x comma y is the link cost from node x to node y. D of v is the current value of the cost of the path from the source to the destination v. P of v is the predecessor node along the path from source to v. So let's say n dash is a set of nodes whose least cost path is definitively known, right? That is the ones for which we have calculated the least cost path. Okay. So initially we start off with this initialization. Your n dash, that is the cost for which information is known, is set to u. U is the node at which this algorithm is running. U, from u to all the other nodes is what we are trying to calculate the path, right? So we are trying to calculate the path from u to all the other nodes in the network. So we start off with n dash equal to u, and for all nodes v, if v is adjacent to u, you mark the distance to v as the cost of u comma v. Now this cost is known to you, right, because these are your immediate neighbors, and for all the others you send the value to infinity. So this is the initialization that we do. Then we run through a loop, right, where we will try to identify the cost of other nodes in the network. So what we do first is, you find some w which is not in n dash, right, such that dw is minimum. So you've got this d of v, right, so you already identified something. Out of that you find out that particular w, that node for which the cost is minimum, dw is minimum. So you add the W to this list n dash, to the set n dash. Now you update the distance dV for all V adjacent to W and not in n dash. Okay, and how do we update it? Using this formula. So you say d of V is equal to minimum of d of V comma d of W plus C of W comma V. What does this mean? The new cost to V is either the old cost itself, which is d of V, or known shortest path cost to W plus the cost from W to V. So I have got now another new node W. So if I have the shortest cost to this W plus distance from plus the cost from W to V. Now out of these two, whichever is shorter, whichever is lower, that minimum value, right, that is what is chosen as the new cost to V. Right. Now this is done, this whole process is now repeated until all nodes are in n dash. So, you keep picking one node from n dash, one node from the set which is not in n dash, and keep moving it to n dash. So, this is the process that is used. We will take a couple of examples to understand this whole thing. Okay. So, let us say we have this graph here, okay, and this is the, we are running this algorithm at u. Okay. If we want a path from u to all these other nodes v, w, x, y and z. Okay. So, initially, right, n dash we said will be initialized to u, and the distances will be set such that to the immediate neighbors which are u, v and w will be initialized with their distances. So, the cost is 7 for this, right, u to v is 7, u to w is 3 and u to x is 5. The others are initialized as infinity. Okay, this is the first step. Now, next what is it that we will do? We will choose, now remember this u that we are giving here is the next hop through which this distance can be reached, or this particular node can be reached. And here this is their immediate neighbors, directly from you can reach this directly. So, that is this P of V or P of W that is being specified over here. Now, out of this, which is the least cost, 3 comma u. So, what we do now is you choose one W, right, and move it to this. So, W is the one which has the least cost. So, I move it to my n dash, and now what is it that I will do? I will now calculate, update the values to V, X, Y if I have a new path through W. Look at what happens here. Now, u to V, we had originally you had a distance of 7, but now W has a distance of 3 and W has a distance of 3 to V. So, if you take this path u to W and W to V, you get a cost of 6. So, you compare this cost 6 with 7 and you find that 6 is smaller. So, you will update this value here, 7 is replaced with 6, and now you know you can reach it through W. So, you put that information over here. Now, there is no change with respect to 5 with respect to distance to x, because this gives you a distance of 5, this is 3 plus 4, 7. So, this is a better route itself. So, 5 remains as such, and there is no information about reaching and about reaching y. You have some new information now, because you can reach this through with a distance of 3, and from here you can reach it with a distance of 8. So, 8 plus 3, 11. So, you are looking at all the neighbors of W. We have looked at W to x, W to v and W to y. So, that will change. There is no information about z because W is not connected to z. So, this will remain at infinity. Now, the next step is you again identify the smallest of these, which is 5. So, we will now pick x and move x to the list n dash. So, uwx is now on n dash, and now we look at the distances that are given from x. Now, x to w we know is 4, x to y is 7, x to z is 9. So, this information is what we will now try to use. So, how does the whole thing get changed now? So, you see that to v there is no change, right, there is no change at all on that side, and to these two are already least cost paths, w and x we do not have to worry about. So, y and z is what we need to look at now. So, to y, x is giving you a distance of 5 plus 7, 12, which is worse than what we already had. So, this remains as it is. Now, to z it gives you a new path which is at a distance of 5 plus 9, 14. So, we have this information. Now, the next step, remember we have to choose again the one which has the least cost. So, we choose 6 here, which is connected to v, and so that is moved to n dash. So, you have u, w, x, v, and now these 3 costs are fixed. Now, we need to look at these 2, right. So, let us look at what all we have now. So, now through v, the u, w, x and v, right. So, u, w, x, now we are looking at v has come in. So, through v, what are the new information I can get? V will give me information to w and to y. So, what is it that will change? So, from v to y, you already have a distance of u to v as 3 plus 3, 6, and now you have a distance of 4 from here. So, 6 plus 4 you have a distance of 10. So, now 11 comma w is updated to 10 comma v, right. So, you have a distance of 6 to v plus 4 to y. So, this becomes 10 comma v, no change with respect to z. So now out of these we pick this, which is again least cost. So now U, W, X, V, Y are added to your list, and now you see what else can be done from Y. Now you have the distance to Y is set as 10, and from 10 now you can reach Z with a cost of 2. So your cost to Z now becomes 10 plus 2, 12, which is lower than your original cost of 14. So that is again updated. So with this now we have got all, now 12 comma Y is the least cost. So you have got your U, W, X, V, Y and Z, all of them have been taken care of. So your algorithm stops here, and you have got the least cost paths to all the nodes that are there in the network. So ones that are circled here are the least cost distance, and the path is specified by means of which is the neighbor through which you have to go, right. So W here, U to go to W, U to go to X, V to go to Y and Y to go to Z, right. So this is the complete information that is available for us. So now once this is available, so you construct now the shortest path tree by tracing the predecessor nodes. So remember, this entire graph is available. On this graph you have to construct the shortest path tree. Once you have the shortest path tree constructed, our entire route is available for us. Now you could have ties that could come up because there may be two paths of the same cost. They can be broken arbitrarily. Normally it is broken by choosing the node which has a lower ID or the highest ID or something like that. Okay. So in this case, this will be the path that we have for all the nodes that are there in this network. So in practice, now we looked at how this algorithm basically works. In practice, the way it is done is that each switch will compute its routing table directly from the LSPs that it has collected. Okay. And it uses a realization of this Dijkstra's algorithm, which is called the forward search algorithm. So we will quickly look at how that algorithm works. Now each switch normally maintains two lists, one called the tentative list and one called the confirmed list. Okay. So tentative list is a list from which it's going to take things and put it. Confirmed is once it is confirmed that it has got the actual least cost path to it. So it will move to the confirmed list. So our N dash, for instance, will correspond to this confirmed list. And each of these lists will contain a set of entries of the form destination, cost and next hop. Okay. So let's look at how this will work. So initially the confirmed list will have just an entry for itself, right. This entry has a cost of 0. Now for the node that you just added to the confirmed list, okay, you call it node next, you select its LSP, and for each neighbor of next, you calculate the cost to reach this neighbor as the sum of the cost from self to next and from next to neighbor. So as we saw earlier, right, same thing. Now if the neighbor is currently on neither the confirmed nor the tentative list, then you add that information, neighbor, cost, next hop information to the tentative list. Okay, where next hop is the direction to go to reach the next node, that node. Okay. If the neighbor is currently on the tentative list and the cost is less than the currently listed cost for that neighbor, then you replace the current entry with this new entry, neighbor cost next hop, where next hop is the direction to go to reach next. Okay. And once the tentative list becomes empty, we stop. Otherwise, you pick the entry from the tentative list with the lowest cost, move it to the confirmed list and return to step 2 and keep repeating this process. Okay. So we look at how this is done with this confirmed and tentative list. We will take a look at another graph here, a simple graph with just 4 nodes. Okay. So let us say I want to find out the path calculation at node D. Okay. So initially first step you will have D is the one which is added to the confirmed list. So D 0 comma dash, okay, there is no distance to it, right. So that is it. So there is nothing on the tentative list. So D is the only member. So now you look at the LSP of D. So D's LSP will have a path to B and to C. So that information is now added to the tentative list. So B comma 11 comma B and C comma 2 comma C, right. So this is added. So next step is you have to choose the one that is shortest out of this. So C2C is the one that is chosen. So in the next step I add the C2C to the confirmed list, and now what is it that I have? I have B11B on this list. Now I will look at the LSP of this C. Now what will I have in the LSP of C? It will give me a distance to A, to B and to D, right. So what we do next is, now you add this information. So you have added this information, which is that you have, okay, there are two things now. We update the information with respect to B. So you can see that B's cost through C is now 2 plus 3, 5. So that information replaces this B11B. So you have B5C as the new distance to reach B, and you have a new distance to A. That is another new information. That is, A can be reached through C at a cost of 10 plus 2, 12. So A comma 12 comma C. So this is added in its tentative list. Now again next step will be to choose the one which is least cost out of this. So B5C is moved here. You have A12C which is sitting here, and now look at the LSP of this node, right, of node B, the one that we moved to the confirmed list. So if you look at the LSP of B, it gives you a cost to A at of 5, and of course the cost to C is already known, right. So this is what we have. So now A12C is what we have. Okay, so you move now the least cost member of the tentative list B to the confirmed and then look at its ASP. So now with respect to A, look at what happens. You have a cost which is, earlier cost we had was 12C. Now you have a cost of B to A is 5, and there is a cost of 10 to reach 5 to reach B. So 5 plus 5, 10 is the cost now to reach A. So now you update this value as A comma 10 comma C, right. So this becomes a tentative entry. So in the next step, you move this to the, this is the only entry that we have. So you move to the confirmed list and we have the complete path from D. So from D, a cost of 2 to C, 5 to B and 10 to A, and the path to which you have to go, the next hop information is also specified over here. So this is basically how Dijkstra's algorithm will work in practice. Do a quick comparison of our link state algorithm and the distance vector algorithm. You find that with respect to message complexity, the link state algorithm with n nodes and e links, order of n e messages will have to be sent. Now in distance vector, remember we only exchange between neighbors, so the convergence time will vary in that case. And if you look at the speed of convergence, your link state algorithm is an order of n squared algorithm, and it requires order of n messages. It may have oscillations. And in distance vector, you may have routing loops, and we also saw that we can also have a count infinity problem. Now this problem will not occur in the link state routing because we have a global view of the network. Now with respect to robustness, if you compare these two, what happens if a router malfunctions? In the link state algorithm, what could happen is that a node can advertise incorrect link cost. But since each node computes only its own table, does not change anything else, only local information is likely to be wrong. Okay. Whereas in distance vector routing, remember that the node can advertise an incorrect path cost, because path cost is what is sent to the other nodes. So each node's table is used by the others, so an error can propagate through the network. In our link state routing, that normally do not take place. Okay. So this is a quick comparison of these two algorithms. Now coming to the open shortest path first protocol, which is what is used in the IP network today. Of course, one of the ones which is used in the IP network today. This works based on this link state algorithm. So it uses all these features that we talked about, that is LS packet dissemination, topology map at each node, route computation using Dijkstra's algorithm. So all these are things that we just talked about. In addition to that, there are a few other things also that it does. So it uses special messages called OSPF advertisements, which are flooded onto the entire domain or the autonomous system as it is normally called. Okay. The domain over which the routing protocol is run is called as an autonomous system. So these OSP advertisements, they are carried in OSPF messages, which are directly carried by IP rather than on TCP or UDP. Okay. So if you look at the OSPF messages, if you look at the header format, you can see that there is a version, type, a message length, source address. This tells you the address from which this OSPF message is generated. We have something called an area ID. We will come to what that is used for. Then of course you can see there is a checksum to make sure that there are no errors. I mean, at least you are able to identify errors. And there is some authentication information, authentication type and authentication. Type of authentication being used and the information used for authentication. Whether using a password or using some kind of a key, that information is specified by these two fields. So you are making sure that the OSPF messages that are exchanged in a secure manner. So we have some kind of an authentication provided for that. Okay. Now if you look at the OSPF link state advertisement message. The main message that we have in OSPF is this advertisement of link state, right. So if you look at that, you will see all the various fields that are there, which cater to whatever you would like to do with this algorithm. So LS age, basically this is like your the TTL that we talked about. There are some options, there are types that are specified. A link state ID, the advertising router's information, the router IP address, and a sequence number. Sequence number is the LS sequence number that we just talked about. There is a checksum again for this message, length of the message is specified, and for every link that is there, you have to specify the link ID and the link data. Okay. So what we have here is that for every link, you specify the link ID and its data. Number of links is specified. So this information that we have with respect to link will be repeated n number of times if you have n number of links. So number of links will be given here, and that many number of not much of information will be repeated here. So link ID, data, type, and then some kind of numerical TOS information. TOS stands for type of service, right. You may have different types of service that you may be looking for or that this particular link may be able to support, and a metric which says what is the cost with respect to the type of service. And there could also be some additional optional type of service information that can be specified, and for more links this information will be repeated. Okay. So, you can see that there is a lot of metric and information that is specified for each link. So, you can choose different metrics for identifying the cost. It need not be based only on a hop distance or just bandwidth around. We could use different parameters for identifying the cost. So, that flexibility is something which is built into the protocol. Okay. And you also have a checksum which is used to identify if there are any errors. Sequence number we have already seen, and link state ID and advertising router together they will identify which this particular node which is sending this information. Okay. So, these are the fields that you will have. Okay. So, if you look at other features of OSPF, basically as we said, it is run internal to a single autonomous system, which is the entire internet. If you look at it as being divided into different domains, each domain is called as an autonomous system. So, within an autonomous system this OSPF will be run. It has support for equal cost multi-path routing. So, that is another additional feature that it has. That is, if there are two paths which have the same cost, right, you can actually send on both paths. You can kind of divide your traffic among both paths. So, that support is also provided on OSPF. And it supports different types of service and type of service based routing. So, you can have different quality of service routes being specified using OSPF. You also have support for variable subnet length. So, you can have the routes being specified along with the destination and the mask. So, you have various subnet lengths that can be specified. Okay. In addition to that, it also has support for multicast. So, what is interesting is that both unicast and multicasting are kind of integrated. So, you have a multicast OSPF protocol which uses the same topology database as the OSPF. Okay. Another very important feature of OSPF is that it has a provision to handle scalability by means of having some kind of a hierarchical mechanism. It actually supports two levels of hierarchy. As we said that within an AS you are running this protocol. This AS in turn is divided into a number of areas. Okay. So, area basically is a group of contiguous networks and hosts, right, and the topology of an area is normally invisible from outside, and routing in the AS takes place at two levels, intra-area routing and inter-area routing. That is how to go from one area to another area, and within that area how to go from one router to another router. Okay. So, this is typically what it looks like. If I have many routers, area A, B and C, so these areas will have something called an area border router. So, this border router is the one which will send information about this area to the other routers, right, and there may be a backbone router which can be connected through a autonomous system boundary router to other autonomous systems. Okay. This is typically the level that you will have. Okay. So, the area border routers, what they will normally do is they will summarize distances to networks of its area and advertise it to other area border routers. So, area border routers talk to each other, and the area internal routers, okay, they will participate in the intra-area routing, and the LSAs, the advertisements basically are within that area. So, they will receive external routes which are broadcasted by the area border router and pass it on to the others. Okay. So, the backbone routers, they will be running OSPF limited only to that backbone. So, you can see that the information that we have, right, it is kind of grouped and segregated so that not too much of information has to be handled by each of the routers. So, area border routers will take care of some information, internal routers have to handle less information than that. So, border routers kind of summarize the information that is required to be sent to that particular area, and the AS boundary routers, they will connect to other ASs. Okay. So, with this hierarchy, what essentially happens is that you are able to reduce the amount of data that is to be maintained at each of the routers. So, that is basically one of the major successes of this protocol. So, some advanced features that are there in OSP which are not there in the RIP protocol is that, as we saw, it has support for security, that is, you have authentication support, so to prevent malicious intrusion, and you have this multi-cost same cost paths that are separated, that are supported. It is not there in RIP, and we also have different cost metrics that can be used to support different quality of service, and you have integrated unicast and multicast support, which is also not provided in RIP. Okay. So, these are some of the special features of the OSPF protocol, and of course, with hierarchical OSPF in large domains, you are able to handle much larger number of routers in the network with the same efficiency or with better efficiency. Okay. So, this is for this reason OSPF is beginning to be one of the more popular protocols, though of course RIP is also used in many networks. Okay. So, to summarize, we have looked at these two things. We looked at the link state routing protocol, we looked at how link state paths are link state packets are constructed and how they are advertised, and we looked at how it is done using reliable flooding, and then we looked at how Dijkstra's algorithm is used to construct the shortest cost path, and then we looked at how OSPF protocol implements this link state routing algorithm. Okay. So, that is it. Thank you.